Hello friends, I Dr. Naresh Sarkar, Department of Physics, Shri Shivaji Science College, Amravati. I welcome you all in the practical lecture. This practical is based on Zener diode, and in this experiment we will going to understand the voltage current characteristics of Zener diode. Friends, before know about the Zener diode, we must know about the diode. Friends, what is called as diode? Diode is nothing but the combination of two p-n junction semiconductor device, which is called as here diode. In this picture, if you observe carefully, we find this n type of semiconductor and this p type of semiconductor, both are diffuse, face to face or back to back, and they produce a new kind of material, or which is called as device, which is known as p-n junction device. Friends, when these two different type of charges or these regions, and p regions and n regions connected back to back, then there must be a junction. That junction is called as depletion layer or depletion junction. In this picture, we see in this p-type semiconducting region, there is some holes are entered, or they produce a layer, and here in this p-type semiconductor regions, there is some electrons, they also creating on layers. So these two layers making a junction, that junction is called as p-n junction, and this type of this block diagram is known as normal p-n junction block diagram for the diode, which is the normal diode. So if you connect this p-n junction in two way, first one is using the forward bias way and second one is the reverse bias way. If I connect this p-type and n-type semiconductor diode in the forward bias, means this positive region is connected to battery plus and this negative region is connected to battery minus. Then this depletion region or depletion width is thinner and thinner, and such that these electrons which is flow through this junction barrier is easily, and they can conducting the current. So diode is working in the forward bias but not working in the reverse bias, means it's flow the current in forward bias but not flow the current in reverse bias. Why it is not flow the current in reverse bias? Because when we connect the battery to the semiconductor diode, reverse bias means this battery negative terminal is connected to diode positive terminal, and this battery positive terminal is connected to diode negative terminal, then the width of the depletion region goes on increases. Okay. So because of that, there is a combinations of the or flowing of the charge carrier from this region to this region is quite difficult. That is why in reverse bias the depletion width got increases, and hence the current is not flowing through this region. Why it is not flowing through this region? Because when you connect this n region to the battery p region and this p region to the battery n region, then the electrons from this battery is attracted all the positive charges, and this negative charges which is attracted by the positive charges of battery, and therefore some electrons which is jump from the n region and they enter to the p region, and some protons or holes which is jump from or transfer or move from this p region to n region, and they produce a thick boundary wall, and because of this thick boundary wall the depletion region got increases. So friend, here we are talking about the Zener diode. So what is the basic difference of Zener diode and the normal diode? So normal diode, this doping concentration is much lighter as compared to the Zener diode. If I am talking about the Zener diode, the doping, it is heavily doped, because in p type this is trivalent impurity, and this n type, that is the pentavalent impurity. So the impurity level is very very high, such that the number of free electrons or free charges is increases or more as compared to the number of free charges available in a normal diode. So just keep it in mind, normal diode it is a lightly doped, and the Zener diode which is heavily doped. So there is a no basic difference, because it is also working as a forward bias as the normal diode work. It is also work as a reverse bias, but the normal diode is not work in a reverse bias. So this type of special diode, which is symbolically denoted like this, so this type of special diode is made for, generally constructed for reverse bias working, or this Zener diode which is act as a voltage regulator. How it is act as a voltage regulator we'll talk in the later part of this video lecture. Okay, so we try to understand why this Zener diode it is work in a reverse bias. See this P region which I am connected to the N type of the battery, and this N region which I am connected to the P type of the battery, or P type P junction, N negative junction, so is connected to the positive terminals of battery. So what happened, it is heavily doped, so number of free electrons, this solid black color dot ball indicating the free electrons, and these are the free charge carriers which is the holes in the N region, and these are the minority charge carrier in the P region. Okay, so keep it in mind, always there is a minority charge carrier which is present in the P region, also in the N region. In case of P region, the minority charge carriers are electrons, and in case of N region, the minority charge carriers are holes. But holes is not moving its place, electrons only enter into the holes, or when the electrons move from its position, they create an electron deficiency space, and that space is called as vacancy, or which is called as hole. Okay, so what happened, when you connect this special type of diode which I called as Zener diode in a reverse bias manner, so there must be the depletion width get increased, but not as much the normal diode. The depletion width is also very high. If we compare this two depletion width, in case of normal diode, when you connect this battery reverse bias, the depletion width is increases, is large, but when you connect the battery in the Zener diode, the depletion width is not too much increases, the depletion width is very thin. So when you apply the potential difference between these two junction, P junction and N junction, so this due to this potential, some electrons which are get accelerated, and this electron when it is accelerated from its position, so this electron is moved from this region, that region is PN junction region or depletion region, and because it is a very thin, and this field which is produced inside the junction is very high, so that is why this field is pushed this electron, and this electron is moving from this boundary region, from this N region to this region, and in this way the electron is flowing, and therefore the current is flowing through the circuit. But if I am talking about this type of junction, means a reverse bias normal diode, this electron is accelerated when you increase the field, but the depletion width is very large as compared to the depletion width of Zener diode. So this electron when accelerated, so this electron get accelerated and moving with very high speed, and this electron is just collide with some of the silicon atoms which is present inside this area. So this electron is collide with the atom nearer to this area, and this atom is ejecting one more electron, and that electron is having some kinetic energy and moving with a very highly acceleration, and that electrons also collide with the nearest atom and ejecting one more electron. So the numbers of electrons which are collide with the nearest atom, and they produce one more electron which is ejected from the silicon atom. So this kind of effect which is called as avalanche effect, and because of that the collision, they produce a heat and generate a heat. So up to a certain voltage we apply input, the electrons is ejecting and collide with the another atom, and they produce a heat, and because of that heat the device get destroyed, and that is why in the reverse bias condition the normal diode is not working, but forward bias it is working. But in case of Zener diode, and because of the thin depletion width, the electron which is not collide and they do not produce a heat, and therefore these electrons are passing from this junction to this region, and this electrons is moving during this circuit. So that is why they could not produce a heat, and the electrons is flowing, and therefore they flow the current. So that is why this type of special type of junction diode, which is designed for controlling the voltage, because at certain level if you increase the voltage of input voltage, the output voltage is remains constant or remains the regulated. So that is why this Zener diode is working. Okay. So basically the day-to-day life application of Zener diode, it is act as a voltage regulator. So you may use so many type of devices in your home, or in your, suppose you are using the freeze, fan, etc. so many. So voltage is regulated. Even though input voltage is fluctuating, the output voltage is always they produce gives the regulated voltage. Okay. So this is the basic idea about the Zener diode. So let us understand the voltage current characteristics of the normal diode, then later we understand the Zener diode. So this is the voltage current characteristic of the normal diode. So this is the forward bias junction, and this is the reverse bias junction. So what happened when you increase the voltage in forward bias? At certain value of the voltage, the current could not increase, and up to a certain value, when you increase the voltage, the current is suddenly increased. But when you apply it in the reverse bias condition, this VZ, that is indicating actually a Zener breakdown knee voltage. Okay, VZK. So Zener breakdown knee voltage. So if you compare about the forward bias also in the reverse bias, so this breakdown region indicating when you connect the Zener diode negative terminal to positive and positive terminal to negative, this breakdown region is happening, but this diode is not destroyed. So that is why this voltage get constant at certain level, and the current goes on increases. So it gives a shunt and regulated power voltage in the output. So this is one more example of germanium based doped diode and the silicon doped diode. So silicon having the energy band gap is 1.12 and germanium is 0.7. So here this knee voltage, or up to when you increase the voltage, the current is not increasing initially, but slowly the current increasing as the voltage is increases. But at certain voltage the current is suddenly goes on increases in the forward bias condition. So this is for the germanium, and this one is for the silicon. Though the same case, if we apply the reverse bias, then also you find the voltage increases, but the current is zero up to a certain voltage, that is the Zener breakdown voltage. When we reach this point, then after the current is increasing very rapidly. So this is called as voltage current characteristics. Okay friends, now we are trying to understand this experiment using this virtual lab. This virtual lab consists of power supply, and this is the keyboard, this is the key, and this is a rheostat, and this is series resistance, and this one is actual Zener diode, and this is load resistance, and this one is the input voltage indicating, and this one is the output voltage indicating, and this is the milliammeter. So friends, in this circuit, this Zener diode is provided in this virtual lab. There's three different values of Zener diode: 5.6, 7.5 and 10 voltage. So I will start this experiment with the minimum values of Zener breakdown voltage, and that is the 5.6 volt. So the thing you should have to notice, when the value of Zener diode we took 5.6, that means if you increase this input voltage beyond the value of 5.6 to 6, 7, 8, 9, 10, this output voltage remains constant, and up to the certain value, means up to the 5.6 volt of this input voltage, output voltage, this milliammeter, the value of the milliammeter or current is very less. But after some time, means the when they cross the value of 5.6 volt, then the milliammeter range is increased rapidly. So you should have to notice this during this performance of experiment. So at initially I just minimized all the value. This is the zero input, the output voltage is 0, and this current is also 0. Now increase slowly the current, input current, and note the output voltage and the input voltage, and note the output voltage, and what is the value of the current across this Zener diode. So start this experiment. So I just increase the value of input voltage and see the output voltage, and just you have to notice this value, how much is it. It is increasing very slowly. See, now the input voltage is 5 and output voltage is 4.95. So input voltage increases, output voltage also increases. Up to what value? Because I am selecting the 5.6 volt Zener breakdown voltage. So now again I am increasing this value. So now this value is reach 5.6. Now see friends, this value is increasing 6.7, 6.8, then it is 6 point something, then it is 7, but the output voltage is fixed and constant. So this is called as a regulated voltage, and now the current is increasing very rapidly. So this is called as voltage current characteristics of Zener diode. Okay, if I am select here, in case of 5.6 volt, I would like to select 10 volt. So that means this value is increasing up to the 10 voltage, even you increase this value beyond the 10 volt. Okay, so let's find this experiment. So now the current is again 0 point something, means current is now very slowly increasing, because the limit, they are not crossed the input limit, so that is why current is also increasing very slowly. Now again I am increasing the input voltage, and note the output voltage. So now see, this is 9.741. so the Zener breakdown voltage here, it is 10, and this current is again, it is 0.46 milliampere. Okay, now the current is reach rapidly, and this input voltage is 10.66 and output voltage is again fixed 9.998. so it is fixed, and this is 11 input voltage and output voltage is 9.99, means it is approximately 10, and this current is now increasing very rapidly. So this is called as voltage current characteristics of Zener diode. So I hope you understand this voltage current characteristics of Zener diode. Thank you very much for watching this lecture.